Now that we've learned all sorts of rules for integration, now we'll actually be able to start applying those rules to real life situations. And one area that we'll be able to apply those rules is when we're dealing with areas and volumes of figures. So in this whole entire chapter, we will be dealing with areas and volumes of all differently shaped objects that we're not used to being able to find the area and volume of. All right, in this specific lesson, we'll be able to find the area of a region between two curves. We're used to finding the area underneath a curve using integration. Now we'll just actually be able to find it between two curves. All right, basically what we're going to be doing, just like what we do, we're taking of when we just have one region, we're just going to take the integral from a certain area, a certain x value to a certain x value. And this time what we're going to be doing, we're finding the area between these two curves. So to get that, we're going to find that I'm going to call A the first point of intersection, B the second point of intersection, and they're just x values. And then we'll always take the curve that's on the top minus the curve that's on the bottom. So if you're looking at it, G is on the top in this one, and F is on the bottom. So this is not always going to be G minus F. It will always depend on which curve is on the top and which curve is on the bottom. All right, to find those points of intersection, we'll just set the two functions equal to each other. If we don't get to use our calculator, we'll have to use a little bit of algebra to figure that out. If we do get to use our calculator, we'll be able to use points of intersection. And if you don't remember how to do points of intersection, you can refer to my points of intersection video in the chapter P video notes. And then from there, we'll just evaluate the integral. All right, so let's go ahead. I've already referred to these first in another video, so I'm going to go right into the examples. I'm actually going to start with example 2. So if you get to example 2, this is going to be a calculator problem. So it says to find the area of the regions bounded by the graphs of f and g. So if you'd like to go ahead and get your calculator out and graph this, and then just come back to me as soon as you're done. I'm not going to actually get out my calculator. I'll just show you what I got when I graphed it. All right, so when I graphed it, I got a parabola going up and then a parabola going down. And this first curve we'll call f. And the second curve, actually this one was f, the one that was going up, and then the other one was g. And we would like to find the area between those two. So we are going to go ahead and set up my integral. I need to go from point of intersection to point of intersection. If we use the point of intersection, this left one is going to end up being 0.26795, and the right point of intersection will actually be the x value of 3.7321. Okay, please notice on both of those I went more than 3 places. If I want to be within 3 decimal accuracy at the end, I definitely need to go out more than 3 places when I start. Okay, and then f of x minus, the one that's on top this time is the one that's upside down, which is g of x, and hopefully if you darkened one of them you could tell that that was the second one, and then minus f of x dx. And then from here, since I do get to use my calculator, I'm pretty much all set. One thing when you're typing it in your calculator, you will get to use Math 9, so go ahead and do that. And then the second thing is, when you do the g of x, that's going to be your y2, and f of x will be y1. So when you type it in, when you're evaluating the integral, you'll be able to do y2 minus y1 instead of actually having to type in the functions, and that will work just fine as you do that. Right, and when you do that, you should get an answer of 13.856. So if you just want to try that on your calculator and see if you got a 13.856, that would be marvelous. All right, let's try another one. This time we're going to do one without our calculator. It says to find the area of the region bounded by the graphs of f of x equal x squared minus 4 and g of x equals 0. So we're going to start, let me go ahead and do my graph. Even if you're not allowed to use your calculator to evaluate it, you will always be able to use your calculator to figure out what this graph looks like. F of x is going to look like this. And then g of x, if I graph it, will go this way. So that was g, and this was f. Okay, and I will be looking for the area in between those two curves, which will be right here. Okay, so if I'm evaluating that integral, I need to find those 2 points of intersection, and to find the points of intersection, POI, we'll set the two curves equal to each other. So we'll set x squared minus 4x equal to 0. Notice it's set up for me to factor. I can factor out an x. And then my 2 points of intersection will be at x equals 0 and x equals 4. So if I set up the integral, the integral will go from 0 to 4. And then the curve that's on the top this time is actually g. It's sitting on top of the f curve. So we'll have g of x minus f of x dx. And then from here, since I don't get to use my calculator on this one, we'll actually put in what the function is. So I'm going to have, it's going to go from 0 to 4 of 0 minus f of x. Notice that I am putting f of x in parentheses because it's minus the whole thing. And then if I rewrite that, of course, I don't really need to pay attention to the 0. This will be negative x squared plus 4x, and it's still going from 0 to 4. Okay, now I'm ready to actually evaluate the integral. So the integral of negative x squared would be negative 1/3 x cubed. And then plus the integral of 4x is going to be 2x squared. And then I get to evaluate it at 4. And then at 0, if I plug 4 in there, 4 cubed is 64, so this is going to be negative 64/3. Plus, if I plug 4 in, so I'll get 16 times 2, which is 32. So that will be the first part. And then minus, if I plug in 0, I will just get 0. Okay, now I'm going to get a common denominator, so I'll have negative 64/3 plus 96/3, and if I put those together, I will get 32/3. So that would be the area of that region. All right, the next one that I'm going to do is actually number 1, so let's back on up here. All right, we want to find the area of the region bounded by those graphs. And again, we'll let this be a calculator problem. So if you want to just take a minute on your calculator and find those problems, that would be wonderful. All right, I know that f of x is equal to, that first one is going to look something like that. Okay, g of x equals -2 is just the horizontal line y equals -2. So here comes g of x right there. And then it also says x equals 1. So x equals 1 is going to be a vertical line right there. Okay, so if I want the region bounded by all three of those, it would actually be this part, this whole part right here. Okay, so if I look at it, I notice that they intersect right here, and then they intersect again right there. And so when I set up my area formula, they're going to go from where they intersect right here. And if you use the point of intersection feature, you're going to get -1.89329. And again, notice I'm going out more than 3 places on that one. And then it's going to stop when I get to that vertical line, which was x equals 1. And then if I look at the figure that's on the top, the figure that's on the top was my f of x, and then minus the figure that's on the bottom happens to be g of x. Okay, and then from here, I did say we could use our calculator, so we will do math 9. When you're putting this in your calculator, since f went first and then g, it will be y1 minus y2 on this one. And if you enter that in your calculator, you should get 8.302. And again, you might want to actually put that in your calculator and make sure you do get that as an answer before continuing. All right, on to number 3 this time. We would like to find the area of the region between those two graphs. And we are going to, let's see, is this going to be calculator or not calculator? We will let this one be a calculator problem. So if you want to go ahead and grab your calculator again, and let's graph what those two functions look like, we will. Okay, if I graph f of x, I'm going to get a picture that looks something, whoops, wrong one, that's going to be g of x. Something that looks like that. So this is going to be f. G of x, I already got it started here, is going to look something like that. I kind of overemphasized it because I did want him to cross up here. So this is going to be g. I think it looks a little bit different than that, but close. All right, and so if we would like to find the area bounded by those curves, notice there actually is an area right here, and then there's another area off to the right side. So we actually want to find both of those areas. So we're going to find the areas of each one separately, and then we will add them together. So we're going to have the area equals, this first one I need to find where they intersect, and then it looks like they intersect at the end point would be 0. So if I use point of intersection on my calculator, I'm going to get -1.6943. Okay, and then on this first one, you'll notice my f is on the top and the g is on the bottom, so I'll have f of x minus g of x. Okay, and then I'm going to add it to, this one's going to start at 0, and this point of intersection occurs at 2.3609. And this time you'll notice for this right figure, the green graph is on the top, so G is on the top and F is on the bottom, so it switches around. Okay, so then from here again you may use Math 9. On this one I would be doing y1 minus y2, and on this one I'll do y2 minus y1. And if I type that in my calculator, we should end up getting an answer. This would be 7.800. This one ends up being 18.916. So if we put those two together, we'll get 26.716 as the area. All right, we're going to go to example 6. This one's a little bit different, you'll notice, because when I look at it, there are actually functions and they are with respect to y instead of with respect to x. On these types of figures, I will go ahead and give you what the graph looks like, so you can just go ahead and copy down exactly what I'm drawing right now. Okay, my first one, f of y, is going to look like, actually it's going to be a sideways parabola that looks something like that, so that will be f. Okay, and then g of y equals y plus 1 is going to be a line that looks like that. Okay, and then if I'm looking for the area between the two, I'm actually looking at this part right here. And you'll kind of notice this is a little bit different because if I'm looking for what's on the top and looking for what's on the bottom, we've got a problem right here because neither one really is on the top or the bottom. So what we are going to do, when things are with respect to y, we're going to turn sideways. And so I'm going to turn my paper, let's see, I'm turning my head to the right now so that I can look at my paper. And then what we're going to be doing on this one, when we're looking at that, instead of looking at top minus bottom when we're doing this one, we're going to be looking for right minus left. Okay, and the other thing that we're going to do is we're going to have our limits, since we're dealing with the y-axis instead, we're going to have our limits be y values instead. So instead of going from something to something in the x direction, we'll be going from something to something in the y direction. So if we set up this area problem, first of all, I'm tilting my head again. If I find this point of intersection, this one would be on the lower point of intersection. If I found that point of intersection that's happening at a y value of -2, and then if I found this point of intersection, it has a y value of 1. So those are, again, y values. It goes from -2 to 1 in the y direction, okay? And then from here, the right function is my f function, and my left function is my g function. So the one on the right is f, and the one on the left is g. And then we should be all set up. Again, since I said we could use our calculator in this one, we'll use Math 9. And since we have f minus g, it would be y1 minus y2. Notice when I actually set up my integral, I never set it up as y1 minus y2 because in the actual problem, they referred to it as f and g, and actually I should not have an x here. I should have a y, and it should say dy. When you type this in your calculator, you will use an x still to type it in your calculator. And when you get an answer, you should get 4.5 as an answer, and you should be good to go. All right, we've got one more problem that we have not done yet, and that is problem number 5. And you'll notice we've got all sorts of stuff going on in this problem, but we'll just graph each one separately, and we should be all set. All right, on this specific problem, y equals 1 over x looks something like this. So that's, and we can call that, I guess, I'm going to call that f just so I can call it something. Okay, and then the next one is y equals 1/2, which is a horizontal line, which will look something, we'll just put it something like that. So that will be, and actually I think this, I'll call this y2, and I'll call this one y1, just to keep it simple. Okay, then it says x equals 0. Okay, so x equals 0 is actually a vertical line, and it's actually just going to be the vertical line right here. And I won't call it y equals anything because it's not a y equals problem. Okay, and my last one, it says y equals 1, which is another horizontal line up here. So that will be y3. Okay, and then if I'm looking for the area that's bounded by all of those, it's actually this area right here. Okay, and then you'll notice again, after this point right here, there's none that are actually on the top. This one's on the top to start with, and then this is on the top after that. So since this is, if you turn your head sideways again to the right, you'll notice that if I look at it that way, the blue one's always on the top and the red one's on the bottom, so we are actually going to switch this one just like we did in the previous example. So when I go to find the area of this one, I'm going to go from a y value to a y value, and I can tell this is just from 1/2 to 1. So I'll go from 1/2 to 1. And then if I'm looking at this, the curve on the right, we're going to do right minus left. The curve on the right is 1 over x. And then the curve on the right is actually just 0. And of course we're with respect to x. Okay, actually I screwed up a little bit there, because if I'm dealing with y values, this is not supposed to say 1 over x. It's supposed to say something with respect to y. So I'm just going to back us up here. We have y equals 1 over x. I'd actually need to get this to say x equals. So the way that I'm going to do that is put a 1 under the y. I'm going to cross multiply. I'm going to get xy equals 1. And then if I'm solving this for x, I'm going to divide by y. So I'm going to get x equals 1 over y. So it did turn out to be the same thing. That is not always the case. But if we're going to use y's, we need to have y values for everything when we do this problem. Okay, I'm going to call this one a non-calculator problem. Let's see how we do on it. I'm going to, first of all, minus 0 really means nothing for me. So I just want the integral of 1 over y dy. And hopefully if we rewrote that as dy over y, we can recognize that as an ln. So this is going to be the ln of the absolute value of y. We're going to evaluate it at 1 and 1/2. So I'm going to have ln of 1 minus ln of 1/2. I dropped the absolute values because those are both positive numbers. The natural log of 1 is 0. And so this would be my answer. And if we're dealing with an area, we should never get a negative answer. But if I were to type this into my calculator, the ln of 1/2 is a negative number, which would turn this into a positive number. Okay, so hopefully now you can find the area of the region between two curves.